Hi, everyone. So it's my pleasure to introduce Julia Lanzillotta for today's tea talk. I've had the opportunity to collaborate with her over the past more than 2 years, and it's been really a pleasure working with her. Julia is a fourth-year PhD student at ETH AI Center, advised by Thomas Hoffman and Benjamin Greve. She is also closely collaborating with Razvan Pashkanu. And her research lies at the intersection of deep learning theory and continual learning, and she works on theoretical foundations of continual learning algorithms, especially in non-stationary environments. And what I personally find very compelling about her work is that she comes to study continual learning from a broader question of what intelligence is. And this has mainly driven her research agenda and also inspired her interest in memory, not only as an algorithmic constraint, but actually from more cognitive science and philosophy perspective, which I find very inspiring. And today she's going to talk about some of her recent work on predictive continual learning. And with that, please join me in welcoming Julia.
Well, thank you, Mandana. I think you could give the talk. Like you definitely spoiled already the first slide. So yeah, so I hope everyone has their tea because it's a tea talk. I have my coffee, and actually I also left in the slides some little tea icons to remind myself to get a sip of coffee and enjoy at the same time. This is the first one. So, okay. So as Mandana was saying, I've been doing research in what I've been doing research in, motivated by one fundamental question, which is a very ambitious question. What is intelligence? And, you know, as some people say, one way to understand something is, or at least there is some kind of understanding in being able to build something, right? So then that's what brings us here, I guess, in AI, the field that tries to build intelligence, right? So I would say one fundamental aspect, and I'm not the only one to say it, actually, there's a beautiful collections of definition of intelligence that I posted here. One fundamental aspect of intelligence is really the ability to learn. And notice how that is different from just knowledge itself that you have after you learned something. The ability to learn is the ability to acquire that knowledge, right? And this is something that if you scroll this collection of definitions of intelligence, you find in many different forms. But what is even learning, right? What is the ability to learn? And one realization that I had relatively early on was that you cannot really, or I wouldn't characterize it as learning if you forget it right away, right? Imagine, I think the name is Dora, the memoryless fish in Nemo, but she kind of learns things and forgets right away, right? So there's, yeah, some kind of, you know, short-term memory and learning, but I would say that a fundamental aspect, or even maybe they are the same thing. I think this is a nice question to discuss about. Fundamental aspect of learning is memory, right? And this is exactly what I set to work on. Memory from an artificial system perspective, which is what the field of continual learning is really about. So I come from a background that is mostly deep learning, computer science. I see things from an optimization perspective. And this means that I study memory in artificial systems and in neural network from this optimization / more theoretical perspective. So what you're going to hear about today is how in neural networks we implement learning with memory, so continual learning algorithms, from a more theoretical perspective. But in general, I also wanted to mention that I think the bigger question of what is memory and and what is knowledge even is still interesting to me. And if, someone hears this talk that is thinking about these questions in terms of philosophy, cognitive science, or neuroscience, let's chat, because I'm always interested in understanding if even our conceptualization of memory in computer science is maybe faulty in some way, right? Okay, so what are you gonna get out of this talk, ideally? Well, if you don't know continual learning and continual learning algorithms, I hope that you're gonna get out of that door and be confident that you know them and you kind of can navigate the field. When you see a new algorithm, you have an idea of, okay, where this falls in place. If you already do continual learning and you're maybe, you're already thinking about these questions, then I hope that I give you some new theoretical perspectives. So I'm not going to talk about any new specific algorithm, but more the foundations of continual learning algorithms. And I think where really the novelty is, where the boundary is and can be pushed. And we're going to start very philosophical, as I like it. And then we're going to do some ups and downs from technical, philosophical, and very technical. So you get some like solid, something, solid and practical at the end. But I ask you in return that you please, make it an exchange. So if you have questions, if I'm losing you, especially, like, just interrupt, say something, anything. And also if you just have opinions, just raise your hand and say it. That would be interesting for me. Okay, so I guess we dig in. So there's no tea on this slide, but I'm actually going to take a sip. So let's start from definitions. What is continual learning, right? And I want to start from definitions because I think that's the first step where there's misunderstandings usually. So if you understand what I mean by continual learning, maybe you have a different idea in your mind, but at least you understand the rest of this talk, right? So for me, the broadest definition that I can think about is efficient open-ended adaptation. And efficient, I think you understand. I think efficient is pretty clear. Open-ended, maybe it's a bit more confused. Like, what do I mean by open-ended exactly? And to give you a concrete idea so that we have a concrete image in our mind, there's a beautiful movie that I really suggest you watch if you haven't watched, that I'm referencing here, and that's WALL-E. So for those of you who don't remember, WALL-E, after there was some kind of catastrophe that hit the Earth, was left alone on the Earth for several years. Actually, I Googled yesterday and it was 700 years. So WALL-E was there for 700 years alone. And I think that requires quite a bit of adaptation. If you think about the world 700 years ago and how much it has changed in 700 years, well, that would have required any system that would have lasted this long to actually adapt to all these changes, right? So this is the concrete image of open-ended adaptation that I have in mind, which is, I would say, quite futuristic for the AI systems that we have today. But this is exactly, and now I'm going to give like really an opinion here. This is exactly what I think academic research should try to strive for, to be not behind, but forward, right? To be in front, to be thinking about those questions that are questions for the future, for the systems of the future, and that really are fundamental. So this is to me what continual learning is that futuristic system question. Okay, now apart from the opinions and philosophical discussion, I would say, so there's quite some heated, I would say, debate right now of whether in-context learning can already do efficient open-ended adaptation in continual learning. And there's actually quite some good people, good papers that are trying to answer this question scientifically. Like, can we get to continual learning just by in-context learning? And I don't want to debate this here, But I want to make it clear that my focus is not in context learning. My focus is in-weight learning, and I think there are some advantages of that. First of all, you don't need an external system that actually has this persistent memory that usually you need with in-context learning, right? So part of the complexity, I think, of the problem in in-context learning goes to the extra storage, the RAG, the whatever extra system that has the persistent memory. And that in weight learning, the idea is just the persistent memories in the weights or whatever you have with your network. And second, you don't really, the inference cost in context learning grows with the context, which has to, be filled with all the information that is needed to fill the task. Well, in-weight learning is really keeping that inference cost constant, ideally. So this is just like, I don't want to open the debate. I just want to mention why I would say in-weight learning is a good option and something worth working in. So what is the setting? I think with this image, I'm trying to represent the most general setting of in-weight continual learning. We have a stream of observations and we have some kind of network. Observations, for now, imagine that it's real time. They come like from the environment all the time. And whenever an observation is processed by the network, the weights of the network, this little connection, will be updated, right? So this means that there's really no final checkpoint, There's no one model, and that you deploy. So it's actually quite a radical shift, potentially, in the way that we do AI that raises so many fundamental questions, right? All that we're building now in deployment, like whether it's how we do safety, we do privacy, how we build guardrails for our system, that is based on having some final checkpoint that is deployed somehow, right? And then some edits are done, usually not real time, where in the interactions with the world and the users, right? So I think there's so many actually interesting, good fundamental questions to ask here that the continual learning literature could ask. And I really encourage anyone that really wants to think in these futuristic terms to maybe go in these directions. One fundamental question that now I'm going to try to treat more technically is, how do we even measure performance, right? Because, I think I'm going to just let the slide say it. So we go into part one. So right now, when you, there's no tea here, so no coffee break. But when you have a good model, a good training learning algorithm, the way you measure good is that you have some benchmarks, right, that you care about. They should kind of represent everything that possibly the model can be used for, and you benchmark the model on those benchmarks. Cool, I mean, makes sense. But what if I want to benchmark the ability to learn, right? Like, what is the performance metric there? When do you know that the model has learned to learn? And this is, I think, one of the fundamental questions of continual learning, and I think recently it's been more in focus in the literature. So the historical answer is just, you measure retention, you measure memory. So you have a system that has to learn a lot of tasks. It learns all of them, and then at the end you see how well it remembers all of them. So there's the stream, you let the system process the stream, and at some kind of end, after a long enough sequence, you see, okay, did it forget everything or not? So this means, I will call this quantity the historical risk. This means technically that we want to optimize an historical risk. So an average loss over all the observations collected from time 1 to time t, the final time. Now, there's been a lot of criticism of this idea recently, and particularly in a line of work that goes under the name of big world hypothesis, which is basically saying that, sure, I mean, this works in some settings, but it will not work, in all the settings, because sometimes the environment is just too big. It's however big your model is, the environment will just be bigger. maybe, you could imagine, as I said, the world 700 years ago, how much it changed in 700 years. Well, it will change still more unless you think that we're at the peak of our society now and everything will remain the same way. So it's actually plausible that we cannot have one minimizer, one checkpoint that works well on this historical risk for all the time to be, right? And this is kind of the big world hypothesis. So what do we measure then? And there's several desiderata that have been kind of discussed in the literature and continual learning. Auto-then retention, like forward transfer, plasticity, real-time performance. And there's a beautiful work from an information theory perspective by Kumar et al. Continual learning as computationally constrained reinforcement learning, that basically makes the argument that if you do optimize for real-time performance of your system, you implicitly will have to, if you have computational constraints, so not infinite compute, you will have to strike a trade-off between retention and plasticity. And this trade-off in particular, what they say is that the optimal retention, the optimal memory, is the memory of what will be useful in the future for the agent. So they say there's some stuff that is useful, some stuff that is useless. Forget the stuff that is useless and keep the one that is useful. That makes sense, right? So now coffee. Yes, question. Thank you. Yes, so actually, this is a perfect question because this is exactly on this slide. So the real-time error, or as defined in the paper, is actually the average lifelong error, is just the average over all the observations in the stream, the performance on these observations. So if it's an error, it's a negative, right? A loss or some kind of negative connotation of performance, or if it's a positive, they actually have a reward in the paper. So you could also measure the performance positively, right? So this is the real time. But of course, it depends on what an observation is, right? The observation could be just one sample, or it could be a full task. For us, the way we interpret it, and I think also the way they mean it, is that you measure performance after every single update of the model. It's not like you can do updates, like an infinite number of updates, right? And you reach convergence maybe, I don't know, after how many steps on some kind of big data set. And then you measure performance afterwards, because otherwise there's no compute constraint that you are enforcing, right? Yes, this is a good question. So this expectation, so the average lifelong error is defined as an expectation over the samples that the environment gives you, right? So this is over the next sample, not the one that you just processed. And there could be a structure in the environment. So the expectation, will actually, the distribution will follow the structure. Or it could be that you're also sampling IID, and then this is equivalent to a test error, right? Okay, so in a recent paper, to retain or to adapt, actually done together with Mandana here. So we asked this question, that we take the framework of Kumar, and then we go to so Kumar studied this question from the information theoretic perspective, and we wanted to study it from the optimization perspective. And we take the gold standard of continual learning, this historical risk, and we take an agent, we call it the joint task learning or joint training agent. I mean, it could also just be a model. Don't think about agentic systems now. That at every step minimizes the historical risk. So it gets a new observation, and then we have the computational constraint that is basically translated in number of update steps, optimization steps that the model can do. And it does, let's say, n steps, a certain number of steps on its objective. And the historical risk objective just pulls things together and averages all the observations that have been collected so far. And we contrast this. So this is the system that retains everything, right? We contrast this with the independent training, independent task learning, which is a system that by design has no memory at all. In particular, to be more exact, our setup is a stream of tasks. So we have a stream of tasks, and also within the task, the distribution is stationary, and within the task, we also have a stream. So we measure performance as the models train on the task. And for the joint training, it just, as I said, the objective keeps adding all the observations and all the tasks together. For the independent training, we reset it at the beginning of each task, so it has no memory at all. And then it just trains on the current observation. So it's a system that just trains on the current task. Okay, so why did we take these two systems and compare them? Well, because really the difference between them is memory, right? Like one, they have the same compute per step. We make the settings such that it's like everything comparable, but one tries to remember everything and the other just cares about the current task and the current observations. And then we ask a bit of in a provocative way, the question, okay, can the historical risk be optimal or always do better than a memory-less system? And the answer is not really, not always, but let me tell you the details about it. So we take the difference, we study the difference in performance of these two options. Remember everything, forget everything. And we call this transfer efficiency. So it's the efficiency in learning that comes from transfer from the past. And it neatly decomposes in a stationary part, which is basically the difference if you could run these optimizations forever, if you could let them reach their stationary distribution in the parameters, I mean, and you take the difference in their performance, that's the stationary gap, which we call instability, plus a gap that is transient and is due to the difference in learning speed. And basically what already this decomposition tells you is that what memory really gives you is just a faster learning, right? A transfer. But in the long run, actually, memory will bias your solution. And so you will actually perform worse on the current task. So if you had infinite compute and infinite time, and you keep sampling from the distributions, also implicitly infinite data, then you don't need any memory. But if you care, if your transitions are very quick or you care about learning quickly, then memory is useful. But to make it more precise, we have 3 results that are qualifying this statement. First of all, we identify what I just said, the critical task duration. So a maximum task duration after which memory is just a liability. So if your tasks are longer than this, then you actually are better off just training on the current data and leaving behind the memory. But also, importantly, we find that this is not, this critical task duration is environment dependent. And you can actually see it already in the equation. So the critical task duration is inversely proportional to this average instability. And the instability, to give you an idea, basically, so it's the difference at the stationary point in the performance of the joint and the independent. What this means is that is the difference at convergence, basically. So it's the optimal solution of the joint versus the independent task learning and the differences between them. So the instability is going to be bigger if your environment, your task set is more diverse and actually maybe interfering. The tasks are really not like fitting well together, right? But if the tasks are actually kind of fitting well together, so they improve the performance on each other's specific set, then instability will be lower, right? And yeah, there's 2 questions now. Yes, you first.
The joint task learning,
Yeah.
Like where it says training science on tasking, like you're still doing joint training, right? Or are you fully training?
Where does it say training on task A? or
the
the line. Yes, yes, it's still joint training, exactly. So it's like a replay. If you know, replay is like replay with an infinite buffer. It's the optimal replay.
so it's like starting from training on, like, is the start of that training from
A previous task. Yeah. Yes.
I'm curious about the word memory,
Mm-hmm.
but all the data, like things so
Mm-hmm.
are you also retain memory of aspect of that? What do you mean by that?
That's a good question. It's more the objective. So what if you think about the optimal of this objective, what the historical risk minimizer is a system that ideally performs well on average on everything, right? That's my definition of memory. It's like something that retains all the past experiences. While the independent training, I say it has no memory because it's actually the optimal, the minimizer of the independent task learning objective is just optimal on this one task and potentially forgets everything else before.
It's like I can imagine these techniques.
Mhm. At the task boundary, you reset. We reset because, yes, because we want to really make sure that there's no, because, when you use this, you warm start from the parameters that you collected, from the trajectories before, there is actually some kind of bias, right, in the initialization itself. So to remove completely the bias at the task, we reset and not in the objective. Yes. With the joint task training, no. That actually is made to have the bias. It's made to remember all the previous experience because otherwise independent task learning will for sure do better because it's actually training on that specific task where you're measuring performance. And if they have the same initialization and one is training directly on that task, that's gonna minimize that loss faster. Yes, so we also ablated, so there's an independent task learning with some warm starting. And actually there it's interesting because of course it depends on the environment. So this is one of the things that I want to say here. How quickly the environment expands actually determines the balance between these two and also whether warm starting is useful or not, basically. Yes.
So you made a comment saying environment changes. It's better to
It's the opposite. So if the environment, if I said that, scratch that. If the environment changes too quickly, the instability is higher by definition of instability, because you're putting together a lot of things that are very diverse, right? If the instability is higher, then your critical task duration is going to be lower, which means that only for very short tasks, it makes sense to have memory. Otherwise, you should not have memory.
for me, like it depends on how similar
Exactly. So this is what instability kind of captures. One way that you can think of similarity is just how well does a model that is really trained on all of them do compared to to models that are trained independently on them, right? If the tasks are really kind of opposing each other, they're kind of fighting for capacity in the model and not constructively, building for each other's performance, then the independently trained models will actually perform better, right? So the instability is this difference exactly at stationarity. Yes, another question.
It's I feel like general like
Uh-huh.
like if all the tasks are sort of like learning for food, like, I'm not phrasing this, I'm fully honest. It feels weird that there's like that much, or like the joint training would be such a bad like thing.
Yeah, so I think it's because I think I got your question. I think it's because we're used to a type of benchmarks where the world doesn't really expand that much. Like you have, even in continual learning, like in this case, we had some theory in a linear setting where we actually could look at how quickly the environment was expanding in terms of the parameter norms of the optimal parameters. And we studied actually 3 different regimes. One is bounded, so you still have different tasks, but they're kind of, the maximum norm is bounded, right? So you're kind of exploring a circle, an area of different tasks. Yes. So for the theory, we have just a sequence of linear regression tasks with some optimal parameters that change, and we can characterize how quickly the environment expands just by looking at this norm, how quickly this basically the maximum norm expands, right? But for actually some experiments, we used, so there's some vision-based classification and reinforcement learning benchmarks. And I mean, for the reinforcement learning, the memory seems to always hurt. So if you look at this last task, so this is the first task, and independent task learning is orange, joint task learning is purple, and the difference, so this advantage of memory is green. The first task, they're more or less the same. They have different optimal hyperparameters, so that's the small differences that you see. And then if you look at the last task, the joint task training, this is the performance on the task itself. So it's what the average lifelong error is actually measuring, the real-time performance. The joint is really slow in learning because it's trying to do too many things at the same time. It's trying to, at the same time, solve one type of behavior and then another and then another. And since it has all of this memory in its objective, you can really see how slowed down it is, right? But in cases where actually, for instance, this clear benchmark is a continual learning vision benchmark where you have the same classes, but they just naturally evolve over time, like the image of a phone. And then you have it 5 years later and 5 years later. And there you actually see how much positive, like constructive interaction there is between the tasks, because there is clearly an advantage in starting off from the previous task solution for the joint task training. And then it is still, like it takes a long time for the independent task training to get, so starting from scratch to get to the good solution, right? So really in the point being here that it really depends on the similarity between the tasks and how much they can be, cooperating in the network, which actually brings me to another point that I also wanted to make from the paper, which this difference, like whether memory helps or hurts, depends also on the model itself. And you need to take into account the model dynamics, even the optimizer parameterization that you use. We try 2 different parameterizations from the same function class, and we get different transfer efficiency curves. So even the parameterization that you use for the model will change the dynamics, which will change whether memory helps or not. So this is just a point that we wanted to make, that the information theory kind of perspective is useful, but like details are important actually. And going back to your question, what we saw, actually, I'll say one thing because it's important to answer your question. So keep that for like 2 minutes. So let's say outcome of this was, okay, there's actually no best strategy, right? It's not always one or the other. Sometimes it's better to have the joint, sometimes it's better to have the memoryless one. So given there's no best, then what should we do in continual learning? And we proposed something in the paper, which we call predictive continual learning. And here, the idea is that actually, so there's one concept that comes from the online learning literature, this online learning with predictable sequences idea, that is that actually you can get much better error rates if you have a model that predicts the future well, which is, of course, like if you know the future, you can learn efficiently. So, we just need to know the future, which is, of course, difficult. But, this, we actually took it as a way to reinterpret the joint task learning and the independent task learning, because you can see them as making different bets on the future. So the joint task learning is kind of making an ergodic assumption about the environment that eventually, you keep sampling from it and eventually it converges to something fixed. It's a bounded environment. So eventually you explore all of it, which means that the future looks like the past. So you should retain everything because you're gonna need it. And the independent task learning, you can instead interpret it from this perspective as making a very pessimistic assumption that there's nothing in the future that you can really know about. So you should just focus on the present, and the past is just bias, is useless bias. So from this perspective, actually, we kind of reformulated or generalized the idea of continual learning to be just in general about predictions of the future. You can have any model, we call it phi here, that conditioned on the history of observation so far tries to predict what the future sequences will be. And assuming the model is it gives you a distribution, so you can imagine a generative model of the future. Then you can sample from it and you get an objective that is different from independent task learning or different from joint task learning, but it's still a continual learning objective according to this view. So this view is it's funny because it's saying the best memory is the memory of the future, but I think it's actually promising. So we tried this in a very, very toy setting. We took the simplest thing to do that was not trivial, and we defined a window agent that just kind of has a window parameter, and this window parameter is just a number of tasks that it keeps in memory from the latest ones. And then we could do some theory with this, and we asked, okay, what is the optimal window? And this is the nice result that now brings me back to your question, which I like a lot. And basically it says that if the world is bounded, so you have, this bounded world, then the optimal window will be the infinite one. So the optimal thing that you can do is just this joint task learning. And I think most of the benchmarks that we have actually have this kind of structure where the world is really not, you keep sampling tasks, but it's not expanding so much, right? So this is why our intuition is that transfer always helps. Maybe we don't have that strong interference in our benchmarks. Or we don't run for that many tasks. But actually we find that, okay, there's a case where, you can make the drift between tasks so big, so the environment changed so fast that actually the best thing is the independent task learning. So we recover also that, and that's an optimal window that is one. But then there's also a case, we've studied 3 cases, a case where it's not evolving so fast, it's kind of a middle ground. And in that case, the optimal window is neither. And then when we implement this, again, orange is independent, purple is joint, and green now is this window agent with this optimal window that is, mathematically derived. And the window agent, of course, always does better than both. So, yes, question. Because, so this is over multiple tasks. So actually you don't see that they're minimizing a task and then starts again. So this is over multiple tasks. And for the joint training, it goes up so much because it tries, to do well on all the tasks. But if they're changing a lot, then it will start like really behaving terribly on all of them. So there's many task switches here. Yes. That's a very good point. Yes, actually, we tried that at some point. It was more explorative, let's say, so we didn't put it in the paper. But we tried actually random orderings, but also orderings that would kind of be more semantically meaningful, also ordering by like coarser and categories and then finer grain. And actually that changes, of course, the behavior a lot because, as I said before, the dynamics are important for transfer. The dynamics is what changes the picture. So if you have an initialization that transfers well, then you're going to learn that task faster, right? And then you're going to have a lower error overall. But if you don't, so the task ordering can completely change that. And I think that's one of the things that we still don't understand. I think there was a question in the back first. Yeah. And sorry, could you repeat because you didn't get it? Yes. I mean, so I think we didn't even put limits in the theory, at least, on tasks not reoccurring because, when we said, for instance, for the bounded environment, we were just saying, okay, we sample from this ball, the parameters, which means that you could sample extremely close, right, to a task that you already sampled before. So really, it's not about, I think in continual learning, we have a lot this idea of, okay, what if we go through the sequence again? We didn't make it about exactly revisiting the same task, but more about, I think it's a more general concept of how quickly the environment expands, right? So how more novelty there is every time, right? If you consider when you revisit the same task, you're basically saying that the novelty finishes at some point, and then you start seeing the same things over and over again. And this is exactly the ergodicity assumption that is kind of implicit in the joint objective, right? So we treated it not directly, I would say, but I think we still did. Okay, yes. I don't know who raised first. Yes. Yeah. Well, I think that's an interesting question. I think, like, instead of just the learning algorithm is important, but also I would add to your question, what about capacity, right? What if I have an infinite model capacity? I have a huge model. Does joint task not, work well? And I think actually, I mean, there was some work that I did in the past about whether scaling helps in continual learning in terms of forgetting, so retention. And actually what we found is that also depends. So it doesn't always help. That's the short answer. But it's because depends on the dynamics. Because when you touch scaling, you also touch implicitly the dynamics of the model. So for instance, we tried to control the dynamics by imposing a lazy parameterization or a rich parameterization, which means less feature learning or more. We found that if you ramp up the feature learning and you scale, actually scale hurts. And I think this is going to your question. It shows that the learning algorithms, the optimization that we have doesn't really, even if you have infinite capacity, it will overwrite in the same spaces the information. It will not know how to disentangle information correctly. While with lazy learning is a bit of a cheat because you're not actually learning features. So it's a limit in which the network learns just because of its size. So it's big enough that it can represent really anything. And in this case, scaling actually helps. So yeah, I think these are important questions, like just in terms of even just the stationary point, right? Whether the stationary gap can be reduced just by model size or optimization. Yeah, that's, I think, good question. Yes.
So I feel like seems like
Yes.
more sort of big one, like
Mhm.
but I was just wondering, like the sort of tasks that I think you did were, I guess, where it's simply set
Mhm.
but I guess on more realistic type of benchmarks for this application, because I feel like it's easy to create one that can think of like very simple. You know,
Mhm. Yeah, so I honestly, I haven't looked extensively into the literature for benchmarks. Just the benchmarks that I know from working continual learning, I would say they're not this kind of like tough benchmarks. But an argument for why diffusive, I agree that it's more interesting. Why diffusive could just be more present is that a lot of natural processes, this is like a random walk process. A lot of natural processes follow this regime. So in the world, actually, if you look around, it's more likely to find a diffusive process than in the natural world than a bounded one. So I think maybe, just intuitively, I haven't looked at it, but if we have a more real world benchmark, realistic benchmark, this would fall more into the diffusive category. This is just the intuition, but I don't know exactly whether anyone has, looked at how quickly the information in the environment grows. This would be the question for the benchmark. Yes.
how do you predict the future? How does
Yes. I think that's the question. How do we predict the future? I mean, ultimately, we're all here to answer this question. Yeah, I mean, I don't think you can, right? Because there's always going to be like no free lunch. There's always going to be some kind of assumptions that you have to make about the world. And I think the game is more having the right assumptions, right? Finding the right bias that somehow works and makes you survive rather than predicting the future correctly. Yes, question in the back. Yeah.
Learning in a situation where I have a certainty.
Right, right.
But I have some reasonable about that.
Mm-hmm. Yeah.
And I don't think that.
Mm-hmm. Yes. I agree. Yeah, just to repeat it for the audience online, what Doina just said is that we don't need and indeed what this equation is saying is not that you need an exact, pixel-wise generative model of the future. I don't think any one of us even imagines the future in that way, right? But maybe a rough estimate that is reasonable enough that it actually will not fail, right? And indeed, I mean, I think this paper is really interesting, actually. They do have bounds. So the error rate in this online learning with predictable sequences depends, on how much you can more or less bound the future prediction, not how exact your prediction is. So exactly what you said. So if you have there's some kind of oscillatory behavior that you cannot predict because it's very instantaneous and random and noisy, but there's a general trend that still gives you some advantage. That's the point of the paper. Yes.
So I think like the underlying point here, but in order to be able to predict implicit assumption that past and in terms of what future. So imagine like it's kind of the past and completely no amount of past.
Yes. Exactly. So that's the minimax optimal, right? So in the worst case, the worst case is when the future is really unpredictable given all your experiences so far. Like right now, the world switches and you are in a completely different alien world where nothing transfers. Well, that's a worst case, right? And in that case, no memory whatsoever helps. And this is exactly what the kind of no memory systems can do best. But I would argue, based on personal human experience, that the past can be useful, past experiences to some extent, in navigating your life, right? Knowing how to act. So I would say that also for agent, artificial systems, this should be the case. Yes. I think I will take a last question, but if you have your questions, keep them because I want to say something else, but you are my selected last. Hmm. So you're saying dynamically, like distributing across the weights? So you mean adjusting the objective directly or the weights? Yes. Yes, exactly. I think that's also an approach. Like depending on kind of what you see from the environment, you say no memory or memory, right? And you could even get finer into this and say, okay, what kind of memory, right? Like the whole past or a part of the past, and you kind of change the objective like this with this selectivity. That depends on the current environment. But I would argue that this is one kind of, it should depend on some model of the future, right? You should kind of have an idea, okay, right now the environment is very dynamic and it's unpredictable, so I'm gonna not optimize on the past. I'm gonna optimize just on the present. And then instead you make another prediction sometime later and you say, oh, now I'm confident that this is where things are gonna go, so I'm gonna adjust my objective accordingly. I think this is a way to approach it, yeah. Okay. I want to make at least one point. I don't know how much time is left. But so I would say all this discussion, what I just presented, and also all the big world hypothesis discussion, it's a question about what? It's a question about what should these systems remember, and I was trying to argue they should remember the future, which seems like a contradiction, but I think that's the best thing we can do. And I think most of the continual learning algorithms in the literature actually answer another question, which is how. So I think all these algorithms are very modular, cumulative in the sense that they just add to the memory one experience after the other, cumulatively, which means that they can be repurposed. I think we don't have to throw them out of the window. I see a lot of people that say, oh, big world hypothesis, forgetting is useless as a question, so we throw out of the window everything that we've done so far. Well, I would argue not. I would say these are two orthogonal questions, or at least they can be treated orthogonally. Maybe there's also some benefit in treating them at the same time, and this is a question. But if we treat them orthogonally, then there's still a value in understanding how to remember whatever it is selectively, for instance, that you want to remember because you think it's useful for the future. And this is why I say continual learning algorithms right now that exist, like you can think of replay. You don't have to replay everything. You can selectively replay, right? If you have generative replay, you can try to replay from a generative model of the future or of something else, right, that you think is relevant for the future. You don't have to use it for the entire past. So I would say replay, for example, but Also, all other continual learning algorithms are really primitives of memory. They are fundamental ways to they say how to remember, and they don't necessarily answer the question of what. I think that's a very wide open question that is very interesting and important. But these two are orthogonal questions. This is one point I wanted to make. Okay, now I think I have a question for you. Should I, like, how much time do I have? Okay, half an hour. I can do half an hour. But how much time do you guys have? Officially until 12. Okay. Well, I mean, I have some more. I actually have, not talked about continual learning algorithms so far. So I have some more things to say. Okay, let's do this. I will try to cover everything, but in a speeding up way. And those of you who, have to leave or are not, cannot follow anymore and you're tired, fine. But let's go. Okay, so now about continual learning algorithms. So from here on, given the qualification that I just gave you, what versus how, from here on, we focus on how. So we take for granted that we want to minimize the historical risk, what I just destroyed just until now, and I said it's not useful. Well, now we take that as an example of what, okay? But as I said before, these primitives can be reapplied to any answer to the what question. And as I said at the beginning, I have a bit of a theoretical perspective. So I think this is not a usual way to present continual learning algorithms, but I think it's a useful way. So this is why I'm going to present them to you in this way. So if you want to minimize the historical risk, one good thing that you could do is to minimize the historical risk, right? So this is what retraining from scratch, and I'll call the solution theta t star, does, right? At time t, you take all the experiences, all the data collected so far, and you retrain on all of it. And there you have your brand new model that actually remembers everything, right? But problem is that as t grows, the cost grows, right? So for instance, foundation models that we have today, if we train them on the entirety of the internet in 2024, and then in 2025, and then in 2026, and then what did we say, 700 years? So 2,724, then, the cost grows, and it grows linearly with t. So I would argue that the goal of continual learning algorithms is actually to offer a cheaper alternative to retraining. So let's say that you have some kind of tolerance on your error, an epsilon approximation of the retraining solution, so an epsilon in terms of excess risk. You want to achieve that with a cost that, if possible, grows sublinearly with t. And I would argue that if we look at this plane, these two axes of excess risk versus compute per step, there's clearly, we can put 2 points there. One is fine-tuning that has the constant cost, right, per step. You just continue fine-tuning on whatever data comes. And retraining, which actually has this linearly growing cost per step, right? But retraining is the optimal by definition here in this section, and fine-tuning instead forgets, right? There's plenty of work now that says, oh, there's forgetting in whatever model. Now, I think the real fundamental question for continual learning algorithms and anyone who's developing these algorithms is this frontier. And in particular, this means that, usually in continual learning papers, you see that there's the performance reported, so they're reporting kind of the excess risk, if you want, but they compare to some baselines that don't have the same compute, necessarily, the same compute cost. So I would argue that actually to do real progress, we need to fix one of the two. So either you have methods, that you match the performance, the excess risk, on the history, and then you show that your method has a lower cost, and that's good. Or you match the compute, you match the cost, and then you show that your method has a lower excess risk. Otherwise, we're not really talking about progress. It could be, you added another point to this same boundary, but the progress is pushing the boundary, pushing this potential Pareto frontier. And it's actually, there's a theoretical question here that is, we don't even know what the physical limit is, right? For continual learning algorithm, we don't know, given a sequence, what the minimal compute that we can spend on that is. And this is an important question to even know what we're trying to achieve. A general note. Now, there's a lot of algorithms out there, and I really think I'm going to try to kind of give you a general introduction to them. So how would I describe a general continual learning algorithm? Well, first of all, this is an optimization first viewpoint, which means that whatever you do in your algorithm, you can describe it in, all the fancy way. What I care about is that you tell me, so what I think defines an algorithm is what it does to the parameters when there's an update. So now this is the general structure, and then I'm going to tell you some examples of how algorithms implement this, what I call step, which is how they update their parameters. Because how they update their parameters, in my view, optimization first view, is what actually causes, whether there's retention or forgetting or whatever else. And so now abstracting away this step, this modification of the parameters, what a continual learning algorithm roughly does is that for every interaction with the world, there's going to be several update steps. And this KT is the number of update steps, which controls, how much compute you're spending for that one observation. And one observation now could be really one single sample from the environment, or it could be a full task because you wait several months and then you update. And then once you've done all your model update steps, you basically, with a different frequency, so it doesn't have to be for every interaction, you also update what I call the storage. So for instance, in replay, the buffer is the storage that comes with the model, with the algorithm, but every continual learning algorithm has its own storage as well. So potentially, and this I call the consolidation step. Now, important note for anyone who wants to do continual learning algorithms, usually, so step, the model update step has a cost. We call it the step cost. But also this consolidation step has a cost. And when you count the total cost per interaction of the algorithm, you should count both. And of course, the step cost is important because it's done several times. If this KT is large, then it's going to dominate. And this is the standard practice. Like task-based continual learning, you get a big data set and you do a lot of steps. So this is why a lot of the literature focused on the stepwise cost. But actually, if you're in a more online setting and you consolidate at every interaction, and maybe you do just one model update, then, actually the consolidation cost becomes important. This is something that is overlooked, I think, mostly in the literature. There's some, for instance, expensive replay methods that select very, carefully the samples to replay, but then they don't account for all the compute that goes into the selection. Because they do the selection once in a while. So fair cost accounting. Now, I think the whole literature, big claim, has two types of steps, which mirror kind of a classic optimization duality. So surrogate kind of steps where you have base is an operator that represents any optimizer. So basically, it can be the optimizer of your choice, Adam, SGD, mu1, whatever you want. So you have this optimization step on the current task loss and some kind of regularizer, some extra thing that you add to the loss. And maybe the ones that already know continual learning could recognize something like replaying here, but also regularization methods like quadratic regularization, EWC, and so on. But there's also methods that instead do a different approach. I call it trust region, they basically optimize only on the current task loss, but then they restrict the update to a subset, a subspace of the parameter space, a region where they trust that the memory is, so that the performance on the past is maintained. To give you some examples, because I've been so abstract so far. So replay, the easiest clear example, the storage is a buffer and it's a surrogate method. Its surrogate is just the loss on this buffer. You can have all kinds of variations on this, and nowadays replay with LLMs is one of the biggest one. You can have generative replay. You can have distillation-based replay. You're still, I would argue, doing some kind of surrogate injection in your optimization and saying, okay, now I'm going to take the steps not on my historical risk because that's not accessible, but on this surrogate version of it, right? And I think this lens is actually important to study and understand these algorithms, like all the generative-based replay algorithms. If the objective is really to remember, then what they're generating should be close. You know, it should bring a close optimization process at least to what the true past would give. But another example is quadratic regularization, where the storage is actually an anchor point, so a point in parameter space, an old checkpoint, plus a curvature, so some kind of positive semi-definite matrix, and the surrogate is really just a quadratic penalty, where this delta theta is the distance to this anchor in parameter space, the difference, sorry. And here you get all sorts of, quadratic regularization methods, but also this connects to the variational literature, so to the more Bayesian methods. And here, it's important to think of then these parameters not as just the model parameters, but all the possible Bayesian, if you have a parametric distribution, the distribution parameters. So you have to be, expand a bit the definitions to fit everything here. Then orthogonal projection methods, maybe some of you know orthogonal gradient descent. Its memory is the past gradients, the gradients of the past. There's also gradient projection memory, which its memory is features from the past. And their trust region, so the operation is to project onto the orthogonal complement of these subspaces. So they say, okay, I think to maintain performance, you don't have to modify, you have to move the weights in orthogonal subspace to the previous task gradients or to the previous task features. And there's also all sorts of variations now, especially with LoRa. Maybe I have time to talk about that. But also masking. There's a lot of masking-based continual learning. The storage is the masks. Trust region is to freeze the parameters that are not in the mask. You could also mask neurons, like more sparsity-based. And then, the trust region is to freeze all the parameters that are relevant for those neurons. Expansion-based methods, they expand the network. So it's basically equivalent to masking, but just on a bigger network. And mixture of experts, you may have different experts for different tasks. And you also have a learned router as an extra storage. And your trust region is just basically given by the learned routing. The routing function is what protects. Okay, so I want to make one more last point. Yes, question. Yeah. Mm-hmm. I mean, knowing how vast the continual learning literature is, I would bet that something has been tried, but I don't know it, which means it's not very broadly, like it's not an approach that is established. But I think it makes a lot of sense. I think that's why I formalize things in this way, because I would also like to encourage people in the literature to think in terms of whether updating or not actually make sense and at which frequency, whether sometimes it's better just to wait, have the current model collect more data, and then later on you update when you understood better what the trend is, right? I think, I mean, there was a bit of a more controversial paper by Ameya Prabhu, that was saying some time ago, oh, if I don't do anything and I just collect data, and at the end, when I'm being evaluated, I train on everything that I collected so far, I'm actually doing better than many continual learning algorithms. And I think it's actually a fair pushback on continual learning algorithms because of what I was saying before about the cost, that we actually, you know, when does the frequency of updating matter? When you actually are thinking about the cost actively, right? When you actually care about every single compute spent on that interaction, right? So sometimes it's actually better not to do anything. And I think these are questions that can be formalized. Like, we could ask, when should we do something, right? When should we update the model? Yes.
That is abstract view of
So I'm focusing on more optimization-based algorithms. There's algorithms that now are based on model merging, for instance, that I'm not covering with this. I think it covers a lot of the literature and a lot of the classics and a lot of the things that work and are in place right now. But it's, I cannot give you an exact percentage, but I would say a good 80%. Yeah. So I think this view helps in several ways. First of all, to understand, you know, if when you are designing an algorithm, if you know that what you want to do is to build an approximation of this historical risk minimizer, then you know that when you're building this step, whatever way you're building it, you actually want the effect to be similar to the optimization on the joint objective, right? So this gives a more principled way to also understand what algorithms are doing, right? So what all these choices are for, and what are the trade-offs between them, because I don't believe there's a single best choice in general. I think there's different trade-offs in terms of compute, the capacity that you use in your model, and how quickly you can update, right? So it makes you, having this general view makes the choices apparent. But not only that, I think a second point is that having this duality actually makes also connection become apparent. So there's some choices. I mean, you could, and I think I have an example in a later slide, take some of these surrogate objective methods and make a trust region version of them. And actually, one of my first papers was analyzing how two methods, they used the same exact kind of approximation of the loss, but one in a surrogate way and another one in a trust region way. They had the same failure modes because they were using the same approximation. So underneath, it's the same mechanism to approximate the historical risk, just different approaches, right? So it's more for understanding and building principled things, from the ground up. Okay, so the last point I wanted to make here is that there's a lot of, I honestly, okay, I'm gonna give my free opinion. I don't like this. There's a lot of LLM papers that now come with, new continual learning algorithms, we do this new thing, and they call it completely different, but actually it already exists in a different form, but it already exists in the literature. There's nothing really new that is being invented, and this is also the whole point why I want to make this abstract, like definitions, because I think we could try to think about new things, we could try to push the limits a bit, and we're not doing it. I see a lot of the same principle reinstantiated over and over, which makes me think whether these are the only principles. I mean, there's some extra things that come from having a big pre-trained models, changes the optimization. There's a lot of things that work much better, like LoRa would not work in a small model, which means if you can do low rank, then you can use capacity better. So there's a lot of nice extras, but you need to contextualize these in the actual fundamental principle on which the model is based on. And so this is why this slide is here, is to say, don't be fooled by the names, because there's actually a long already history, and trying to understand these methods should be based also on this history. Okay, so same primitives of memory everywhere. Okay, one last thing that I want to say, and I'm really gonna use my last 10 minutes, but this is, I think, actually the coolest, more technical part. So good for you that you stayed. So I will try to argue that one principle that I saw through the years kind of reappearing in many different methods is functional invariance. So to keep the function on the past the same as you change the parameters. And this is a form of memory, sure, but it's a very strict form of memory. It's like, to give you a concrete example, when, let's say you have a robot that learns to navigate a room, there's some obstacles, it has to move, and then it learns another room continually. Great, continual learning robot. But if it's with functional invariance, that it has memory of the past, then when it goes to the first room again, it will navigate in exactly the same way. No matter how many new rooms it has explored, it doesn't really change its behavior on the past, which is a bit weird, right? It's a bit restrictive. One would argue that there's memory of the past as long as you can successfully navigate that first room, right? But you don't need to follow always the same path, have always the same behavior. So yeah, but I will now try to prove to you that a lot of algorithms implement this strict form of memory, which also raises the question of whether we should try to do something different and think of other ways of implementing memory. Okay, so very briefly, a first way to implement this is you do a first order approximation of the loss. Sorry, you had a question. Yeah. Yeah. Mhm. Yeah. A great question, and this is why I love questions and talks, man. It's great. Yeah, it's I had never thought in this way, but I think continual learning and robustness are very related. It's about how your function behaves on other data, right? That you haven't seen, and no, I think I haven't seen, but I'm here. I admit my ignorance, but
There's also
cool. So there are some things that exploit.
but I don't think they are using the blueprint of
Okay, I think I'm gonna ask you to send the paper over. Okay, thanks for the question. So if I have a first order approximation of my function, so in neural network, we have a Jacobian times the parameter displacement delta theta, then my principle of invariance is just to keep this product here small, right? That's pretty straightforward. So here there's the surrogate loss that EWC gives you. And EWC works with anchors, as we said before, previous checkpoints that work really well. And here it basically penalizes the difference from the anchor proportionally to the diagonal entries of the Fisher information matrix. Now you can write this more generally just in this quadratic form with any matrix Q, as long as Q is positive semi-definite. And actually there's a paper now 4 years ago that says, yeah, you take a lot of these quadratic regularization methods, concluding EWC, and Q is basically, they show an approximation of the Fisher, or more in general, an approximation of the generalized Gauss-Newton matrix. What does this mean to have this choice? Well, the formula for the generalized Gauss-Newton is the following. You have an expectation over the Jacobian with Hessian Jacobian product, where the Hessian is the Hessian of the loss with respect to the network function. So if you suddenly plug this formula inside this general quadratic formula, moving things around, you get that it's basically penalizing this one product, Jacobian parameter displacement, with the metric given by the Hessian. So the metric is dependent on the loss. But what does this mean? I mean, as I said before, this is exactly the displacement for the linearized network function. So what the penalization is really doing is it penalizes change in the linearized network function. So if your model is close to the linearization, then this is a good regularizer, right, for getting functional invariance. And actually, this is the point that I was saying before of connecting, using this duality to connect methods. So EWC, or in general, you know, this quadratic regularization methods, they use the generalized Gauss-Newton, have this kind of soft penalty on this product, on the linearized function change. But if you transform it into a hard constraint, so you just set it to 0, for instance, with a projection, there you go and you get orthogonal gradient descent and all sorts of variations of it. And these are two instances of the same approach, but just one is surrogate-based and one is trust region, right? And this is what I was saying, my first paper was showing that they have the same way of breaking, like they're very sensitive to high learning rates, both of them, for instance. But okay, now I'm gonna use the term trust region a bit differently. Now, for this specific linearization-based method, the trust region is the region in parameter space where this linearization is correct. So you would say, or correct, is let's say, less than epsilon wrong. So you would say within this trust region, they actually can achieve their goal, right, to minimize historical risk. But we also know that regularization, but also OGD, they consistently underperform replay, for instance. And I think commonly held idea in the literature is that this trust region is just too restrictive. Like you're gonna get out of it with your optimization dynamics very easily. So we asked this question in a recent paper, and actually the truth is a bit more interesting, is that it's not that the trust region is too restrictive, so there's no good solutions for the new disks there. But it's more the regularization has an implicit bias that systematically makes the optimization leave this trust region. So it has the bias due to just how the structure of the Jacobians are, they're very overlapping, and I don't have the time now to get into the details, but it will systematically, the optimization process will systematically make it leave the trust region. And so is there any hope for this kind of regularization-based methods? Well, surprisingly, we found that replay in the tasks, in the sequences with very high interference, not only minimizes also the regularizer, so this Jacobian, so it's in the null space of the Jacobian, the trajectory, but it also does it keeping the trust region error very small. So it actually navigates this kind of functional invariance subspace for the function, which is accurate even at first order. And this is surprising in several ways, which I think makes replay a very worthy object of study. I think we just don't understand the bias, the implicit bias in the optimization of replay, but it's really not just doing what we put there in the objective. It's not just finding a solution that is minimizing all of the task's losses. It's actually, since its starting point is a minimizer of the previous task's losses, it actually has a strong bias in its optimization that will probably restrict the final solution set for replay. And I think this is shown in the fact that, for instance, here there's the change in the output for the replay function, and it barely moves the output on the past. So replay does this functional invariance, but even to a stronger extent, it does it with even first order, in a first order approximation validity region. Now I'm gonna skip this, but basically let me just say there's methods that also do the invariance exactly. GPM is one of those, and we have some results that basically show how you can basically do a trade-off between how much you allow your function to change and how much capacity you allow the new task to get. Also all the masking, network expansion. If you do mixture of experts, we have one expert per task. So basically like really routing separately stuff. You also get functional invariance. I think I want to get to this, and this is my final point. That is that, let's say that there's a true invariant manifold of your function in the parameter space. Then things like regularization or GD, they approximate it with a rough approximation with a tangent plane, which is the kernel of the Jacobian at the previous task's anchor. And things that are more exact, like GPM, actually approximated with much smaller subspace because they run out of capacity very fast. It's a much stricter constraint, but it's actually accurate. It's exact. So this means that they actually do achieve exact invariance in the network function, but they have to restrict the parameters change much more. And I think this brings two kind of failures that we see. For instance, for regularization, the approximation of the invariant manifold being too coarse gives forgetting eventually. And instead for GPM, orthogonal LoRa methods that build on GPM, the approximation being too strict leads to capacity loss. Eventually, you don't have capacity to solve the new tasks. So I would say that this brings to there's some clear next questions to ask along these lines. If you really want to achieve this functional invariance, then let's study the functional invariance manifold. Let's have better descriptions that are maybe more accurate than a first order, or maybe less strict than what the GPM type of restriction is. But also let's design the bias, the optimization bias. So one thing that I didn't say is that in the paper where we showed that regularization fails because of an optimization bias, you can actually play with that a bit and you get much better performance in regularization, which is great. But this means that you cannot just design a regularizer that is an approximation of something and not care about where that approximation is exact, right? And how to bias the optimization in this region. We need to design both together. But I think the more fundamental point that I want to make out of all of this is that, do we really want to build systems that have functional invariance as their fundamental principle? Can we think of a way to go beyond it, to have the so-called backward transfer? So you learn something new and actually you change and improve your performance on the past. Positive backward transfer. And I think the reason why we cannot explicitly build this is that we don't understand if you give me a new task and I have a model that has learned previous tasks, I don't know whether they're going to interfere or positively actually collaborate, right? Whether learning the new task is going to improve my performance on the previous one. And this is the fundamental question, is whether when learning together, sharing the parameters is actually going to bring positive transfer, and when is it actually going to be interference? It's a question that I think has a fundamental optimization angle to it. So it cannot be answered generally for any model, any architecture. But I also think it's important if we want to go beyond functional invariance and have systems that we trust. Okay, thank you. This is, I mean, just to say thank you to my first, before I thank you, to thank all the people that have worked with me, because, you know, research is not done in a vacuum. Ideas are always in exchange, always together with people. But yeah, thank you for listening, for staying until now. It's been a pleasure. And yeah, just as a summary, I think continual learning asks two questions. How